In this example, we will be talking about how complex numbers can be used directly in order to solve or represent a particular situation. It is very seldom that complex numbers themselves are just going to be the solution to a very basic problem. It tends to be part of the puzzle or something that you need to understand in order to evaluate something higher. In this particular case, though, we have that complex numbers can be used in a variety of fields, including representing and understanding electronic circuits. In an AC circuit, the real component of the complex number is considered the amount of resistance in ohms, and the imaginary component of the complex number is considered the total amount of reactance, also in ohms. The complex number itself, then, is the effective total resistance in the AC circuit, where the modulus of Z is the measure of impedance in ohms, and the argument of Z is the phase angle between the current and the voltage. If you'd like to look more into what each of these terms mean and more of an understanding of the electronic circuits, I would encourage you to dive into that concept a little bit more on your own. This problem is just to give you a quick example of where a complex number can be used and what the values of the complex number are referred to in this particular field. For this example, we have, let us say, that a given circuit has a resistance of 45 ohms and a reactance of 12 ohms. From the description above, the resistance of 45 ohms, that is corresponding to the real components of the complex number, and the total reactance in ohms, that is corresponding to the imaginary component of the complex number. We're going to find the impedance and the phase angle. The impedance is the modulus, whereas the phase angle, that is the argument. So even though this is in another term, this is using different words to express these values. In a complex case, we're working with a real and imaginary component, and we're trying to find the modulus and the argument. They just have different names in this particular case. If I write my complex number then, the real component plus the imaginary component times I, that means I can write this complex number as 45 plus 12I. That would be my complex number to represent this circuit. The impedance is the modulus. So we just need the modulus of Z, which means that we're going to be working with the Pythagorean theorem. By using the Pythagorean theorem, we are simply going to take the real component squared plus the imaginary component squared and take the square root of that result. That will give me the impedance in ohms. As per the question, we are going to round this value to 2 decimal places, and I'll use a calculator for that purpose. So we want the square root of 45 squared plus 12 squared. That gives me approximately 46.2 decimal places 57. The phase angle, on the other hand, that is just the argument. So we're going to be calculating the angle measure, in this case in degrees. In order to calculate that, we typically use arctangent of the imaginary piece over the real piece, or in this case, it would be the reactance over the resistance. So that would be 12 divided by 45. As both these values are positive, we do expect an angle measure that would be in quadrant 1 of the unit circle, so we can keep it as it is with just arctangent of 12 over 45. We do not need to adjust the angle measure in any way. But we do need to approximate this. So again, we will use a calculator for that purpose. Inverse tangent of 12 over 45. Do make sure that your calculator is in degree mode, as it does ask us for a degree measure. We have 14.93 degrees. Those would be my two answers for this question, for the impedance and the phase angle for the circuit.